Welcome to Chapter 4, Algebra 2 students. I'm excited about this because we have some pretty serious real-world application in this chapter. All right. So when you hear exponential, what comes to mind? That's a good question to think of. Hopefully you're thinking, oh, well, I know what exponents are, like 2 to the third. That's an exponent, otherwise known as a power. So an exponential function is going to be a function where instead of having something like this, that's a quadratic, that's exponential, where the actual exponent is the variable, is what we're going to be manipulating. So here we have a pretty standard definition. An exponential function has the form y equals a times b to the x, where a is not 0, and the base b is a positive number other than 1. Let's break down that sentence right there. Y equals a times b to the power of x. Why would we say a can't be 0? Well, because if I did 0 times whatever this is, I would just be getting 0 all the time. That's boring. That's not a function. It's not going anywhere. Why should we say that b needs to be something other than 1? Because 1 squared, 1 to the 1 millionth. It literally doesn't matter at all. I'll just get 1. So it would be kind of pointless to have it be 1, so it's got to be something else. Right? We call b the growth factor because that's kind of determining how much we're growing by every time we change that input, right? That when you have a growth factor that's 2, right? If your thing is y equals 2 to the x versus y equals 3 to the x, what grows faster? The 3 does, right? 3 times 3 times 3, right? 3 cubed is 27. 2 cubed is only 8. So the larger this number, the faster you're growing. So here's an important vocabulary word, the idea of a parent function, as in it's the basics. So what's the general sense of these graphs? The general sense would be f of x equals b to the x, so kind of like 2 to the x is probably one of the most standard ones. But even no matter what b is, so if we just have it as 2 to the x, 3 to the x, whatever, you'll always have these points in common. 0, 1, because anything to the 0 power is 1. And at 1, you'll be at whatever the number is, right? 2 to the first is 2, so this could be 1, 2. 3 to the first is 3, so this could be 1, 3, depending on what the growth factor is. And then it will continue going up, 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 forever and ever and ever. And here we'll keep going down, 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 down. But look at this. This is a big, important piece of today's lesson, the word asymptote. What is it? Well, here's what it looks like. Here's horizontal. Here's vertical. Do you guys think you could tell me what it is? Pause the video and think about it for a second. It's any line that a function approaches but never ever crosses. And exponential functions all have one. Y. Let's talk about y. Let's talk about y. If I did this, y equals 2 to the x, no matter how far I go backwards in the negatives, right? 2 to the negative second would equal 1 over 2 squared, so 1/4. 2 to the negative third would be 1/8. 2 to the negative fourth. All right, I'm getting ahead of myself because I know I'm about to write 1 to the 16th. Right? So I keep getting smaller, but I never, ever get to 0. All of these exponential functions will have that. There will be some value that they never actually get to. Right? No matter, even if I made this negative a million, I'd be 1 over 2 to the power of a million, which would be really small, but it wouldn't be nothing. It'd be 1 over this really large number, but even that isn't nothing. So I would never cross 0. Now the asymptote is not always 0. That's using sort of the that parent function, it'll always be 0. We'll talk about how the asymptote can shift and all that other stuff in a later video. Right now, you just need to worry about that it exists, have a firm understanding of what it is, right? So here we have a great little example, right? Y equals 2 to the x. And I would call that pretty much your standard um, parent function here. 0, 1, 1, 2, 2, 4, 3, 8, and then going and getting smaller in the other direction. So this is still something we can graph. We can still make XY charts like we've been doing all year, right? Just because the X, the input, is now in the power position doesn't mean that we can't still approach this any other way or any differently, right? So let's talk about word problems. So I want to talk about really quickly at the end of this video the idea of exponential growth models. So this chapter is great because there's lots of real world stuff. Right? When things increase by a certain percent each year, it can be tricky to think about what that really looks like. What it looks like is this. Y equals A times 1 plus R to the power of T. So there's a lot of different variables in here. What does each mean? A is your initial amount. What do you start with? We're talking money. You start with $100 in your bank account. You want to know how much it grows? We're talking people, right? Population increasing. What does that look like? R is the growth factor. Why would I add it to 1? It's an important part of the video to pay attention to, right? If I tell you that your bank gets you 3% return on your $100, if you do 100 times, 0.03, because that's 3%, to the power of, however many years it's been, 5 years, 10 years, doesn't matter. You're only going to get the amount of money that you're, making. Right? You're not going to get the total of what's in the account, right? If it's been 1 year at 3%, when you do this, you'll get $3. But is $3 in your account? No, $3 is what you made. That's what you added to your account. But $3 is not in your account. So what you want to do instead is take that percent when you write it as a rate and add it to 1 because I'm growing. So I will be bigger than 1. So it'll be 1.03. The 1 covers the fact that you will still have the original $100. And this covers how much you're gaining. So you'd wind up with, 100. That makes sense that after 1 year, I'd go from $100 to $103. It's an important piece to understand if you're going to get these word problems correct. So here's a great one. This is us, right? 94,166 people living in Quincy. I might have made this problem my first year teaching, so I don't know how accurate that is. But if we assume that the population grows at 1.5% over the next 5 years, what will the population be in 2025? Here's my work right here. My initial amount, that's my initial population. 1.5% looks like this. 1, because I still have 94,000 people living here, and then 0.015. And I want to raise it to the power of 5. Let's go 5 years into the future to 2025. 1.015 to the 5th power is 1.077. So basically that's saying, look, after 5 years, you've actually gained 7.7%, right? Which is a weird thing to think about. Like, because if I do 1.5 plus 1.5 year after year for 5 years, you might be thinking, what did I have? There's 1, 2. I might have gone up by 7.5%, not 7.7%. That's why exponential growth is cool. No, it is bigger than that because every time you're adding to the population, there's now more people living in the city, which means 1.5% is now being taken out of. Right now, it's 1.5% of 94,000 people, but next year there's more people. So 1.5% of a larger population. So it's bigger every time, which means by the time we're done, it's not 7.5, it's actually closer to an increase of 7.7, which may not seem like a lot, but it is, right? This is when we're talking about people. Certainly when we're talking about money, all right? So we can see in 2025 about this many citizens. So we covered a lot in this video. Covered the basics of graphing and the basics of growth word problems. And that's what we'll focus on for a little bit before we get into things like decay, right? If things can get exponentially bigger, couldn't they also potentially get exponentially smaller? Yes, we'll talk about that. And we'll talk about shifting graphs up and down, right? Because sometimes it's like standard with that asymptote, but like, what if I said move the graph, over to the right a little bit and up a little bit? You can do stuff like that. We can shift the graphs over. We'll talk about all that stuff in other videos. For now, you're good.